Hi, it's Mr. Kaladi here, and today we're going to be going through the lesson 4.2, which is all about friction. This is actually two sections in your textbook, so there's a bit of reading to go with this lesson. We've already talked about friction, but you should go through the lecture slides and just see some more details. We're going to give you a formula for friction. We're going to talk about how static friction and kinetic friction are different. One important detail is that static friction can be higher than kinetic friction. You figure if you push something very lightly and it doesn't move, there's a little bit of static friction pushing against you. If you push really hard and it doesn't move, there's a lot of static friction working against you. But there's a point all of a sudden where you do push on something and it starts moving, and then you'll see the kinetic friction actually ends up being an amount that's less than the highest value of static friction. There's also a lot about car tires and how they work. You again go through the slides, you'll see some more images and some more explanations. One thing that always confuses students is the idea that we need friction when a tire spins. Imagine this is a slippery surface with no friction at all. When that tire turns, it just turns on itself. It doesn't contacts the ground, but there's no friction, so it just spins and spins and spins. It would be like if you were stuck in mud or stuck in snow. So we actually do want friction when we drive. And what happens is if there is friction between these two surfaces, well, the tire would push on the street, so it exerts a force on the street, and then because of Newton's third law, the street pushes back. And that's the kind of forward force you need for the tire to move forward on the ground. This is the same with your shoes, right? We want friction on your shoes because as you push on the ground pushes on you so that you're able to move forward. Newton's third law. There's also some interesting safety ideas and things about ABS brakes, so make sure you read through that part in the slides or the textbook. Okay, let's get to the fun stuff. Let's get to these questions. Mr. Clyde pushes a huge rock with a force of 430 newtons. If he pushes any harder, the rock will move. So I'm pushing really hard on this rock, but it's not moving. The mass of the rock is 83. Calculate the coefficient of friction between the rock and the ground. Okay, so again, you could draw a little sketch. So I'm pushing some massive rock like this, right? So if I have a free body diagram of the rock, so I have a force of gravity. I have the normal force, which should balance it. Now I'm pushing in this direction, so we're going to call that the force applied. And the rock is not moving. So we know that whatever amount of friction is fighting me has to be equal. That's the force of static friction right now. Again, static friction can be very high. Do we know anything? Well, we know the mass is 83 kilograms. We know that the pushing force is 430 newtons. We'll say forward. Okay, is there anything I can figure out? Well, I can figure out the force of gravity. Now let's make some definitions here. Let's call down positive, and let's call to the right positive. So this is going to be plus 430. Okay. I can figure out the force of gravity, which is mg, which is 83 times 9.8. That gives me 813.4 newtons. Okay, and we need to calculate the coefficient of friction. Okay, so we know that the magnitude of Fg is equal to the magnitude of Fn. So we know that Fn is equal to 813.4 newtons up. And we know that the magnitude of force applied is equal to the magnitude of the static friction. So I know that static friction is equal to 430 newtons backwards. Now I can use the formula that we learned in this week's lesson, is that the force of static friction is equal to mu s Fn. And here's the important thing, these formulas don't have direction. You don't write the arrows over the, you could either write absolute value signs or you don't write the arrowheads over the F to show that they're not vectors. The static friction, it technically can be up to this amount, but I'm going to write equals. I'm solving for mu, the coefficient of static friction. So, okay, I know the static friction force, it's 430 US, and I know the normal force, it's 813.4. When I divide these two, so I get 430 divided by my answer, I get mu S is equal to 0.5286. This number makes sense. Usually the coefficient of friction is between 0 and 1, right? You can see all the different coefficients of friction in this table, and it depends on the surfaces, but 0.5 is something that's very reasonable. Therefore, the coefficient of static friction is 0.53. So to solve for this, I had to know the static friction force and the normal force. Both of them I got from my free body diagram. Okay, question 2. A 1,150 kilogram car is driving on the highway at a constant speed. If the coefficient of kinetic friction is 0.25, calculate the friction force and the applied force. Always helps to draw a free body diagram for any question you have in these chapters. The first thing we know is there's a force of gravity acting on the car. We know the car is 1150 kilograms. There's also a normal force that balances that. Again, I could put the little marks there to show that they're the same length. And then, okay, now the car's driving at constant speed. That means that left and right, those forces have to be balanced as well. I know there's friction, so because it's talking in the question about some sort of kinetic friction, so it's going backwards. So there must be some force balancing the kinetic friction. Well, this would be whatever's forcing the car to go forwards. This is the force applied by the engine. But these have to be the same because we're moving at a constant speed. Okay, so what am I trying to do in part A? Find the friction force, that's Fk. Okay, well, I know from this week's lesson that kinetic friction is equal to mu k Fn. Well, I know what mu k is because it was given to me in the problem. I should write it somewhere. Mu k is equal to 0.25, so that's my coefficient of kinetic friction. So now I just need my normal force. I don't know what it is. Oh wait, I know that my normal force is the same magnitude as the force of gravity. So I can write that. Why don't I do that down here? We know that Fn, or the magnitude of Fn, is equal to the magnitude of Fg, which is equal to mg, which is equal to 1150 times 9.8. So I get 1150 times 9.8, 11,270. And again, this is the magnitude I'm interested in. Remember, this formula doesn't have arrowheads, or you could put the absolute value bars to show that you're just looking at the magnitude. Okay, so now I have enough information. I have 0.25 times 11,270, and that gives me 2817 newtons. That's my friction force. And then again, there's no direction here, but for my final statement, which I'll write in a second, I know the friction force is backwards because of my free body diagram. But we're not done. We have to find the force applied. Well, again, this shouldn't be too difficult. If my force of friction is 2800 to the backwards, then for this to be a constant speed, my force applied also has to be 2800 but forwards. So I'm going to write my final statements here. Let's just write all as one final statement. So therefore, the friction force is 2.8 times 10 to the 3 newtons backwards, and the applied force is 2.8 times 10 to the 3 newtons forwards. There we go. So hopefully this lesson was okay. Using those two formulas, they're basically the same formulas for static friction and kinetic friction, and you're able to get a bit better idea of how friction works. Until next time, we'll see you later.